Sir, we are live now in YouTube also. Hello. Hello.
Hello.
Hello. Sir, YouTube में भी link का live है गला sir. हाँ sir.
Excellent.
6-7 people are watching now.
अच्छा.
Bishant, can you change the layout of YouTube to what? Change the layout to spotlight.
Sorry, sir. Are you telling something?
You can change the layout of YouTube to spotlight.
Acha, okay, sir. Okay.
Okay. Just go to your Google Meet. There is a button on 3 dots. So there is an option called layouts. Click on that and choose spotlight. That's it. Okay. So that the other things will not be visible. Yeah. Yes. Yeah. That's fine. Thank you.
So, hello. Am I audible, Jana? Hello, Jana.
Yes, sir, you're audible.
Actually, Dr. Das is already joined. Hello. Hello, Dr. Das. Hello.
Dr. Sumit Das, good evening.
Hello.
Hi.
Hello. Hello, Dr. Sumit Das.
Hi. Yeah, I'm logged in.
Welcome. Actually, here is a good. Our evening is here. So, can we spell it good evening or good morning for you?
It's good morning. Actually, it's actually very early in the morning. Thank you.
So, it is morning there over, I think.
Yeah.
So, it is evening over here. It is evening already 5:30. So, thank you very much for your. We are disturbing your very early morning nap.
No, it's nothing like that. Thank you. Yeah.
Okay. So, in a very short while, we can start our this particular presentation. But I require your consent because this presentation has to be recorded for the official set.
Okay. Yeah. Sure.
Thank you very much.
Yeah.
So, actually, this is we are actually discussing about the Google Meet platform, but this particular presentation is being streaming through live through YouTube actually.
Okay.
Our graduate, undergraduate students, both final year students, they are actually given this link, this YouTube link, for to participate in this particular presentation. And we are actually all the members of the faculties, professors, deans, and other students, research scholars. They are actually coming in this Google Meet platform, also in the YouTube platform, wherever it is possible. So
Okay.
we
Yeah.
are
That sounds good.
we are with us actually. Gyanranjan Patra is there, and he is actually coordinating all this particular presentation on the behalf of the department. So let's wait for another 2-3 minutes. Hello,
Yeah, that's fine with me. Yes.
Jana.
Yes, sir.
So we'll be starting within. Are you recording or am I?
I've not started recording. I'll start recording after.
You have already started recording.
No, sir, I have not started recording. In 2-3 minutes, we will start recording.
Okay.
Sir, I think we will start. It's 5:30.
Jana.
Yes, sir.
Hello. Let us
Yes,
start
sir.
with proceeding.
Okay, sir. So let me start the recording first.
Thank you very much, class.
Yeah. No
I
problem.
hope I have not disturbed you much
No, not at all.
during this morning.
Yeah.
Sir, we are live now.
Okay, thank you. So let us start the proceedings.
Okay.
So a very good evening to one and all present over here, and very good morning to Dr. Das over who is staying over there in the Venture. And actually, we are privileged to have with us Dr. Sumit Kumar Das as the inaugural speaker of this particular weekly webinar that is going to be conducted in every week at the Saturday almost. And he is going to present a topic on human-robot interaction. And briefly, I can introduce, I have the privilege to introduce Dr. Das. Actually, he is a graduate from our Bishant University of Technology. He has completed his graduation from the PUT in the year of 2010 here. And then he pursued his MS degree in University of Texas and awarded degree in 2015. And later on, he completed his PhD from the University of Louisville in 2019. His expertise and interest is robotics and control systems, physical and social human-robot interaction, mobile robot path planning. And from 2010 to 2013, actually, he was in the Accenture Service Private Limited in the Pune or Bangalore, I think. Okay. So actually, and he is supervising, presently he is supervising one PhD and one MS student. He is a research scientist in the Center of Louisville Automation and Robotics Research Institutes at the University of Louisville. And he has received so many awards for my mobile micro robotics assembly challenge held at International Conference in Robotics and Automation in the year of 2014, 15, 16 and 17 in Hong Kong and Singapore. He has 5 peer-reviewed journal papers to his credit, including 2 IEEE transactions, one in IEEE transaction automation, science and engineering, and the other one is IEEE transaction robotics. He has 15 peer-reviewed conference paper to his credit, and he has already 2 patents in his name. So I hope his presentation on this particular human-robot interaction will throw some light in the direction where we can actually have some idea how a robot and human interaction can be helpful beneficiary to the social and human welfare. So over to Sumit Kumar Das, please. Dr. Das, please.
Thank you. Let me see if I can figure this out. Okay. Okay. Please let me know if this is visible.
Yes, sir, it's visible, sir.
Okay, perfect. All right. So good evening, everyone. Thank you so much for inviting me for this talk. I guess I'll just start with introductions and then we'll get on it. So basically, the topic of the presentation is human-robot interaction. The idea is that how many ways are there to interact with a robotic system, how many types of robots are there, and what kind of control systems are required to basically facilitate these kind of interactions. That would be the topic of our discussion today. So my name is Sumit Kumar Das. I'm a research scientist at Louisville Automation and Robotics Research Institute in University of Louisville. So today, let's see. Yep. So today we're going to discuss about the robots, the type of robot that I have worked with, namely the social robotics and the collaborative robotics. And then we'll move on to the interfaces that are required to basically how do you interact with the robots, what kind of machines are or machine interfaces that are required in order to have the human intent being implemented for the purposes of controlling a robot. And Also, during this talk, I would be covering the Neuroadaptive Controller that was developed as part of when I was doing my PhD research. It was about how a controller can harness the power of neural networks and be able to basically control and understand the system dynamics of a robot. And to basically conclude my talk today, I'll go over an adaptive robot nursing assistant. This is a robot that was created by the research group here at University of Louisville to assist nurses in a hospital setting. And we'll go over various I would say functions and various modules that were developed for this robot. All right. Before we start, let's introduce like what is robotics. So a very prevalent idea in the robotics community is that a robot is any machine that can sense, plan, and act. So that if it can sense through sensors, right? So like, for example, you have camera, LiDARs, IMUs, the inertial measurement units. So through these sensors or sensory, I would say, sensor data that the robot gets, it basically tries to understand the environment that it is working in. Then the planning is based on what kind of controllers, what kind of state machines, and what kind of neural networks that are implemented to understand, make sense of those sensor data, to plan the path forward, right, and to achieve a common goal. And the last part, the act part, is the actuators. So it can be any of the actuators or manipulators. So you have a robotic arm, you have the wheels to move from place A to place B. So all these combined will make a robotic system. That's one of the ideas that we have in how to define what is a robot. Now, there are many kinds of robots, like ranging from drones, UAVs, to ground vehicles, autonomous ground AGVs. And in this topic here, I'm going to just concentrate on the robotics that I have worked on, which is mainly the social robotics, industrial robotics, and the collaborative robotics. So social robotics. So this is a unique area of research where you have robots that look like a humanoid, right? That you can see in this slide here. So the idea is that they can, they're called social robotics so that they are intended to basically have social interactions with their users, so that you can basically have a cordial, I would say, conversation, or you can have facial expressions. And you can also, the other area of research is also how you can do facial mapping. Like, for example, if you were talking or you have a speech, like there's a speech, I would say, augment this lip syncing to the speech modules, right? Now, I would like to direct your attention to the last picture here. I'm not sure whether you can see my mouse, but the last picture is the Xeno robot. So this is actually a very unique robot. It's a very expressive robot, which is a very childlike attributes. And this is actually currently being used to study the effect of introducing robots in the treatment of autism, where the idea is that kids, autistic kids, or kids on autistic spectrum, they're not that socially, they don't like to socially interact. So a robot would be able to intervene and basically teach them social cues, like, for example, handshake or hand wave, all those things that come naturally. This robot is being used to teach those social skills. Another part of the robot that I was fortunate enough to work on is the Philip K. Dick, or the PKD robot that you see on the left here. This is actually one of the first version of the Sophia robot that has been created by the Hanson Robotics team. It's actually one of the first, not one, but it is actually the first robot to get a citizenship from Saudi Arabia. So it's the first robot citizen of the world. And the research area here is, how do you make it more human-like? So the problem here is that there is this thing called Uncanny Valley. Now, what does this mean, the Uncanny Valley? It says that the theory says that if the familiarity or the features, the facial features of a robot, if it starts to come closer to looking like a human, people are not going to accept it. And that's why you see this dip here. Let me see. So there's this dip here that you see. That dip is because it became too close to becoming like a human, like the facial features, the eyebrows, and all the movements are like human. So the idea is how do you bridge that gap? So there is also this paper that Dr. Hansen had published. It's about if we make it more intelligent and move it like a human, like try to move it like a human being, we would be able to bridge that gap and make it more acceptable to the users. So the video that you see on the left here is basically, it's a very old video. I was working on the robot to basically do a facial mapping. There is a camera in the front. In this video, you'll see it's basically, let's see. So you have this camera. This is a Kinect camera in the front, where you have a user sitting in front of it, and then you do a mapping, a one-to-one mapping as to the head motions, the facial expressions, as well as the eye motions in it. So this is done by taking in the skeleton or the facial features by this Kinect camera, then you decode it, and then move the robot according to the data that you're gathering. Now, this is well and fine because this is a one-on-one mapping. But what do we have to do if we want to move it like a human, right? So that's where we come across the neck-eye coordination. Now, let me start the video. Now, in the neck-eye coordination problem, we have this idea that if you have a humanoid robot, right, and you're trying to track an object, so it's a combination of motion of your eyes as well as the neck, right? So how you move your neck and how you move your eyes, there are some laws that actually regulate how human track it. It's called the Dontus law and the Listings law. And that's how the human basically track. And if we implement these laws, this mathematical formulation on these robots, we can guarantee that they're also tracking the object just like a human would. So use the video on the bottom left is actually the setup. It's actually showing the setup that we had, where we had the markers, those are the bright balls that you see here. So those markers are being tracked by a IR system, by a camera tracking system. And then basically as the head and eye were moving, the goggles were actually tracking the eye motion. And as the eyes and head were moving, it was being tracked. And then we basically mapped it and saw if what we coded into the control structure was actually being followed by the robot or not. Now, let's see. All right. So let me go back a little bit. So apart from these kind of research, the other research is also how to do lip sync, where you basically, how do you move your lips to match the words that are coming out of the robot's face. So the idea is that you have visemes is what they're called, the shape of the lips. Those are called the visemes. And how do you match those visemes to the phonemes? Phonemes are the pronunciation or the vowels that you're speaking. And how do you match them? It's a very complicated problem to solve, because there you'll have to take care of the timing of your robot has to be exact to the word that is coming out, and also to make sure that the motion of the motors that is moving the lips is synced up to the words that are being spoken by the robot. Now, moving on to the industrial robotics. Now, because of some proprietary research, I'm not going to go deep into this topic, but let me just introduce what industrial robots, like what are the challenges or what are the research problems that we're trying to solve here. So you see here, there's a big robot. It's a Denso robot. It's a big 6-degree of freedom arm that can basically move in a rail and then do pick and place tasks. But the problem is not doing the pick and place tasks. The problem is bin picking, where in a bin, which you see this bins, if this is full of items in a hospital, in a industrial floor, how do you specify which object to pick, and how do you, I would say, sort through the cluttered workspace? That's a huge problem that everybody in the industry is trying to solve right now, where you're doing bin picking, and the other problem is how do you do accurate picking? What that means is if you have an assembly line, how do you do basically exact picking, where you basically pick up an object, and then when you're trying to assemble it, they have to be exactly in a specific orientation at a specific position. Now, having said that, let me move on to the next one, collaborative robots. So there's another problem that that occurs with the industrial robot. It is that when you're working with these fast robots, it is not safe. You can get hurt. You can get actually seriously hurt while working with these robots. Now, how do you make these robots collaborative so that a human and that robot can share the same workspace, right? So that's where we introduce the collaborative robot, right? Where you have these robots that can sense, or that have not sense, but that have a arm that can actually not hurt a robot, not hurt a user if it is operating in a same workspace as a human being. Let me see if this video is running. Give me a second. Okay. So also, I would like to direct your attention to the bottom right, is where you also have an industrial robot, but you have a skin sensor that the user is touching now to make it more compliant, so that it can sense users, or it can sense any collision and basically react to it. So that is also one way of making it safer to share the same workspace as a human being. Whereas on the left, this is a PR2 robot, or personal robot 2. It was made by the company Willow Garage. So here the research was, how do you sense user forces and user intent, which I'll get into it later part of this presentation. Also on the top, there's this Baxter robot. I'm sorry, I don't think the full video is coming up here, but this is also a collaborative robot which can basically do pick and place tasks, and but still be safe to use around users. Now, with all these robots, we need some kind of interfaces. Now, the research that I'm doing right now is in the collaborative human-machine interface. What that means is what kind of interfaces are available. How do you make it more collaborative so that the user will have a good experience interacting with the robot? Now, we have direct input devices that we can use to control a robot, ranging from a tablet, ranging to a joystick, or even keyboards of a computer, right? The other idea is how to use non-traditional input devices, such as this Myo band that you see here. This band here is actually, you wear it on your forearm. It takes your EMG data and gives out the EMG reading, right? So how do you understand? Because there is no up, down, left, right in such a device, right? You can wear it any way you want to, and you can basically start outputting data. So how do you map that data into controlling a robot, right? So for this purpose, this idea was born, where you have an input device which is non-traditional, which has no specific direction for that matter. And then you input that data into a learning algorithm in a neural network that will learn how to control a robot and basically output actuator commands. So the actuator commands will keep on moving the robot. But then we also have something called a performance feedback, where we take either user input or a controller input to basically understand if the performance is good or not. And if it is, then you keep on like changing the weights. If it is not, sorry, if the performance is not good, then you keep on changing the weights until it becomes acceptable to the user to have a good interaction with the robot. Now, to demonstrate that, so for example, we had a turtle bot. That's what you see here. This is a turtle bot. And the idea was, how do you move it from point A to point B using that Myo band? Now, what you see here in the video is where the user is actually wearing the Myo band on the wrist. And the data is being basically collected. And that obviously that Myo band has no sense of direction, because you can basically wear it in any orientation. And still through continuous learning, through continuous improvement, through reinforcement learning, you're able to control the robot to move from point A to point B. So it's actually a learning, I would say, process for both the controller as well as the user, because the user is also learning if they move the arm to slightly to the left or slightly to the right, how does the robot move, right? So it's basically a collaborative learning process as well. Another idea of using EMG is when you have, this is a very old research project where basically if you have EMG sensors, so there is this head wearable EMG sensor that this user is using. This basically takes in your EMG signals of the head. And how do you map that to the motion of the robot? So the user here is basically clicking his eyes or basically making facial expressions or motions that will affect those changes on the robot. This this is a small robot called Neptune that was used in the lab to basically gather the data and process the data in order to map it one-to-one between some, I would say, facial features or some EMG signal to the motion here. There's also tactile sensors. It's actually a very, I would say, it's also a very vast, I'm sorry, let me mute the sound. Yeah. It's actually a very vast area of research where you use tactile sensors to make or sensorize the robots that are typically not aware of the, I would say, environment or the workspace that they're working in. So here you see there are tactile sensors on this side of the robot. And as the user touches them, the robot basically moves away. So the idea is if you collide, you move away. But I would like to direct your attention to the part where, depending on the orientation of the robot, the tactile sensor was able to, let me play this again. The tactile sensor was able to understand the orientation and change the behavior of the skin. So if you see, if right now the user is clicking on the front and back, it's going front, back, left, right. But as you move the orientation of the robot, the same sensors can be used to move it in a different direction, because the direction of the robotic arm has changed. So this is where you actually take in kinematics of the system into account, so that you can actually plan your path depending on the data that you're receiving. So with all these interfaces that we have, and with all these robotic systems that we have, we had this proposal, or we had this idea of using neural network inside a controller, which we call the Neuroadaptive Controller, or NAC. Now, before I move on to what is NAC, let me basically dive into what a controller does. So for people who are not from the controls background, a PID controller is a very widely used controller where you tune your P, I, and D constants, and then you try to control the, I would say, a trajectory tracking using a robot, right? Now, what happens is you have to tune it. That's one idea. So you have to spend some time to tune your parameters. The second problem is that it is very system dependent, right? So you cannot just use those parameters and just use it on any other robot. You have to tune it again and again. So if you have developed a solution, you basically want to port that solution into another robot, you have to get back to tuning again. Now, also the system dynamics are like anyone who's aware of the Lagrange equation, the Lagrangian equation, where you have the mass matrix, Coriolis term, and the gravitational term that basically govern the dynamics of a robotic system. How do you account for all the disturbances, right? So, I mean, PID is pretty good in terms of adjusting to those disturbances, but if you want to create a non-system dependent or a non-model dependent controller, how do you account for all these system dynamics change? Because if the robot has a lopsided weight and it's going to move in a weird position, how do you make sure that it moves to exactly the location you ask it to and exactly the orientation you ask it to, right? You might start, it all depends on your feedback as well as your controller and how much, if there is an error, how fast it can drive that error between the desired position and the actual position to zero. So for that purpose, we have this controller, the Neuroadaptive Controller, where you have this neural network in between your human-machine interface as well as the robot. So the controller takes in the desired trajectory from the user, and using another actually best feature about this Neuroadaptive Controller is that it's not model dependent. It's a model free controller. So you basically, these neural networks actually learn the system dynamics on the fly. You do not have to pre-train these neural networks. You do not have to gather data to train them. Those are not required in this case. We use the feedback trajectory to train it on the fly while operating the robot, and it's very fast when it converges its weights. The second idea was that how do you make it portable, which is basically the model-free nature of it. And then also, once it does that, it also actually has been proven to be stable in the sense of Lyapunov, where you basically, because of that reason, the weight updation, like in any neural network, you have back propagation or some other algorithm how you want to update the weights. But this Neuroadaptive Controller does not take that into account. They basically, what they do is update the weight using equations that actually follow the stability law. Now, why was the Neuroadaptive Controller necessary? Because if we want to get into the realm of physical HRI, physical human robot interaction, or PHRI as it is called, where the human and the robot are actually holding on to the same tool, right? And they're trying to accomplish the common goal, and how a robot can help the user accomplish a common goal. What you see in this video here is the robot and the user are basically trying to traverse a figure 8 on the floor, and they're actually both holding on to the table here, right, the cart. Now, there are force-torque sensors at the rest of this robot, due to which it is able to understand the user forces. And with this force-torque sensors data, it's able to understand the direction and the speed of the object, and it's able to also basically move along with the human. This robot is really heavy, but the user here is able to move it in a very easy fashion. Now, in such problems with the physical HRI, NAC is very important, because when you have the Neuroadaptive Controller, they're taking in the physical interaction data through force-torque sensors or any sensor for that matter. Then it tries to understand the intent, which is a human intent estimation part, which is also something that we'll get into in a couple of slides, and basically move and share the load, the workload of the user. Let me see. Okay, so this is what the Neuroadaptive Controller looks like, the NAC system. This was actually proposed in 2017 by Ishura Ranatunga as part of his dissertation, PhD dissertation, where you have a desired, like you have a desired tracking or a velocity where you have position and velocity, and you also have acceleration, and you feed it into this neural network that is sitting right here before you send out the torque commands to your robot system, and have a feedback going into the neural network as well, so that you can train the neural network as the robot is moving. I won't go into details here, but if you have questions later, I can answer them. But this is where you have a lot of modules which takes care of the robust control here and the tracking loop in the system. Now, what was the benefit of using that? Now, you see in this robot, in this video, like you have this PR2 robot trying to move with a weight at the end of its gripper, right? So that's why you also change the dynamics of the robotic arm, because you're adding a weight to the end effector. But with a PID, you see there are disturbances. So it's not accurate when it's doing a wave motion, whereas during a neuroadaptive fashion, it was more stabilized, less, I would say less errors while trying to follow this motion. I'm sorry. So there was also this, let me see. Yeah, there's also this collision experiment that was conducted, where you have this bottle of water, and then if you knock it, how does that neuroadaptive controller react versus the PID controller? And you'll see the result shows that PID, the neuroadaptive controller was actually, the performance was really better than the PID controller. Yeah, I don't think we have the yeah, I don't think we have the result in the video here. But anyway, so now that we have established that we have the neuroadaptive controller, how do you also combine the human intent estimation? Right. So human intent estimation is where you have a human data, like user data through user forces, like FH that is represented here, and you have a human intent estimator that uses neural learning algorithms to learn and understand and also estimate what's the direction and what's the speed, velocity, and direction that a user wants, and basically use the robot controller or the neuroadaptive robot controller to move it in that direction to share the load and basically work with the user, not against it. So here you have to know what's a common goal. So and this was actually, let me run the video before I go into this. So here you have this, this was actually a paper that was published in the Transaction on Robotics. And this was the setup here. So let me talk a little bit about it. So you have the PR2 robot and you have a subject. And both of them are actually holding on to the same tool piece. That's this pen-like structure here. And the idea is that you're moving it from point A to point B on a 2D structure. And if the robot can do some of the work that the human intends to do, right? So that was the experiment with this control structure. So we had this, I'm sorry. So we had this trajectory that we wanted the robot and the user to follow. So the reason behind this is that you have a pure X and Y motion while you're trying to traverse this square path. Then you also have a combined motion of X, Y. It's a linear combination of X, Y to move from in a diagonal fashion in this diamond shape. Also, you also have nonlinear function where you have this circle where you have X squared plus Y squared. So you have a nonlinear function here. So you do a circle. So we tried to test out all these three areas and see how the NAC would adapt and behave in these conditions. Now, so this is how it operates. So you have the user and the robot holding onto this toolbox, and they start moving through the path. Through this path, and then try to understand if they can, if there, and we were trying to understand if there is jerk, how is the quality of motion, and what kind of accuracy we achieved through this kind of a setup. So also during this experiment, we did a forward and a backward motion to also understand if there is any discrepancy if we do that, to also understand, to basically test it out in a whole, the entire controller. So I'll just skip on ahead to the results part a little bit. Yeah. So this was basically how it was plotted and how they performed, right? And this is where we plotted it. We tried to see what was the error in the path trajectory tracking in the entire thing. So you see, you go forward and then you go backward with this robot system, and then it's the same thing you do it with the diamond as well as the circle. So I'd like to skip ahead to the results portion. Okay. So let me pause here. Okay. So this is one of the metric that we use to understand the quality of the interaction, which is the squared jerk. So jerk is basically your measure of how your interaction was when you when the robot and the user were all holding on to the same piece. Now with this results, we found that our robot performed comparable to other standard controllers, but the differentiating factor was that this controller did not need any training. It's a model-free robot. It's a model-free controller that can work on any robot if you just plug and play, learns the dynamic system and just starts. So you don't have to tune it like you do in a PID controller. So that's why we also use this square jerk, and we saw that jerk was actually mitigated in that fashion. The other one was how much force the user was applying versus how much force the human was applying. And basically, the idea is that the force C, the FC here, the force by the controller has to be more than the force of the human, so that it compensates for the work that is intended to be done. So using this metrics, we found that our controller was really good at estimating human intent, and basically performed comparable to other controllers. Now, that basically concludes the part where we have the human-robot interaction and the interfaces. Next, I'm going to move on to the robot that was actually part of my PhD dissertation as well. It's the adaptive robot nursing system. So I wanted to also, as part of this talk, I wanted to introduce what this robot does and why it is beneficial in a healthcare system, and what we're trying to do with it. So this adaptive robot, and we actually have a patent pending application on it right now. So this robot here is intended to work in a hospital setting. Now, in a hospital setting, it's very cluttered. So you have to understand the cluttered environment, operate in a cluttered environment. And in a hospital, real estate is everything. So how much space the robot is taking up, it has to understand where to move, not to hit patients, not to hit nurses or any other people walking by, and still able to perform some of the labor-intensive tasks, so that it frees up nurses to do patient-centric tasks. So we have nurses are nursing workforce. They're typically they're overworked, and basically because they have a lot of work in terms of taking care of patients, as well as more labor-intensive tasks where you do and fetch items like towels, medicine supplies, or anything that requires them to move from point A to point B constantly to gather equipments, right? So the idea behind this project was that you create a robot that can take care of some of the routine tasks that is labor intensive, so it frees out nurses to do more of the patient-centric task. Now, this robot here was actually created ground up in our lab at University of Louisville. In here, we have this omnidirectional base. It looks like this black and red thing here. and it also has a 6 degree of freedom arm. So it has a 6 DOF robotic arm that can do pick and place tasks. So it's basically like a mobile manipulator. It can go from one place to another and manipulate objects and basically pick and place objects from point A to point B. Now, along with that, there are also other sensors attached to it. So basically, there is this handlebar that you see here, has a 4-stalk sensor, and it actually has the capability to work like I would say, a robotic walker, where the user can basically apply pressure on it, and that will basically support the user as well as walk the user and help in the process of ambulation. Now, it is actually equipped with a lot of sensors, such as bump sensors, which basically is the last, I would say, is when you basically bump onto a person or any object, you basically have a stop, so that the robot doesn't go beyond a hard surface or someone it's accidentally bumping into. Then we also have IR range sensors as well as ultrasonic sensors to basically range the walls and the environment around the robot. And we also have the IMU sensors, which are the inertial measurement unit sensors, which basically gives you this sense of direction and if there is any drift while operating the robot. So these things can be taken care of by taking this data into consideration. There's also a LiDAR sensor in the front. I don't think you can see this in this. Oh yeah, I think it's hidden behind this. So a LiDAR sensor is what you typically use in a autonomous ground vehicle system to map it's a laser radar, right? So you basically map the area around you, and it helps you navigate autonomously in any environment, as long as it can basically map the features and everything. So this is a video basically showing the capabilities of the Arna robot as well as the development process of the Arna robot. So we have this mecanum wheels that you see in this video here, which can basically be used to make lateral as well as forward and backward motion. So you see, it can also make diagonal motion because of these mecanum wheels that are in place. And let me give it just a second. And then it basically has also a mixed motion, so it can actually do complex, I would say, maneuvering because of the use of these special wheels. It's actually very powerful. It's also capable of carrying a person if there is a walking process going on, and if the patient doesn't want to. Let me pause the video here a little bit. Walk anymore, they can actually carry the patient and then drive it around like a Segway in a hospital environment. What you see here is we were actually doing a test on all the sensors that we have, and these basically show the sensors reading that can be plugged into the controller to understand the environment here. This is a custom tablet app that was also developed these are like the divots that you find in an Xbox controller, so that you can move the robot, rotate the robot around, as well as get the data. We also have a camera, which basically have a camera feed and basically understand what is going on in its environment. So here, this was very initial test when we had built the robot, and throughout the video, you'll see the building process of the robot. We iteratively kept on making changes. This is where the robot is able to carry the patient, in this case, our team member, to basically take care of the addition of the weight on the robot and still be able to move and be controlled. What you see here on the screen right now is the autonomous mapping or the navigation stack that was created for the robot. So this is a hospital testing floor that we went to the School of Nursing here at the University of Louisville to test out this robot. And through this, I'm not sure why this is jerky, but through sending commands from a remote, I would say, console, where you send it from point A to point B, it's able to move in that direction. Now, what happens if you add an user into the mix? So you're autonomously navigating, so you're trying to compensate for the added weight, and you're still able to autonomously navigate in this whole scenario. So we actually conducted tests where we had nurses or nursing students come in and use this robot and give us feedback. We had a technology acceptance model where we try to understand if they are inclined to use it in the future, if it is introduced into the system, which was overwhelmingly in a positive, we got positive responses for this robot. Now, let's see if I can move it around. Now, because it is a mobile manipulator, the another idea of using this robot, it was during the COVID times when you have the arm, you have the mobile manipulator, right? And how do you use that to disinfect any workplace environment, right? So that was one of the idea behind doing this test, where we basically used UV wand as well as a sprayer system that was attached to the arm of the robot, and we were able to basically move it around in our university facility and basically test it out to see if it can spray on commonly touched surfaces, like you have doorknobs, door handles, tabletops that are commonly used. But yeah, I think here you can see the LiDAR in this video here. So there's a LiDAR here that I was talking about previously. Anyway. So you use this UV wand to shine the UV wand light on a surface, whereas you also have this sprayer system that you can spray on surfaces to basically spray disinfectants like isopropyl alcohol or isopropyl alcohol and a hydrogen peroxide mix. I apologize. I think the video is a little bit tricky, but I think I can send a link later because these are up on our YouTube channel, so we can send a link there. Let's see. And for that matter, we were also recognized locally in Louisville to basically, for all our efforts that we were doing to basically work with the robot and use the robot to do this disinfection. Now, before I close out, I would like to talk about some of the robotic competitions that actually help in. So this is for people who want to get into robotics, students who want to get into robotics. A very good idea of having this robotic experience is also getting into robotic competitions. Our team had participated in this Amazon picking challenge that happened at the international conference, the ICRA conference, and we also had this DJI mobile manipulator or mobile robot competition. So these competitions actually give you hard deadline, like timelines that you have to follow. This also helps you in basically learning new skills and having the problem solving, I would say, knack to solve problems when you're troubleshooting, because there'll be a lot of troubleshooting when you're trying to prepare a robotic system for such competition. Now, the one on the right is also what I wanted to just show you the video where we had this robotic arm, which is actually used for rehabilitation purposes for people like a prosthetic robotic arm. And I had this infrared sensor that was able to take in my arm skeletal. And by decoding that skeletal structure, we were able to also move the prosthetic arm. So basically it can mirror a healthy limb. So if you have like a sensor where you can move your healthy limb, the prosthetic limb will also mirror it. So if you're trying to pick up an object or you're trying to make a gesture, all these things are possible through these kind of sensors. Now, so for collaborative robot, I'd like to go over what are the research areas and what are the research ideas in these I would say in collaborative robots or the PHRI. So the idea is to make the human robot interaction safe but usable. So it shouldn't be slow that it's not usable in a definitive sense, but it also has to be safe while working with with a human user in the same workspace as the robot. Now, it also has to do with some kind of a load sharing so that it actually estimates the intent of the user while doing this PHRI that I showed during the course of this talk. How do you share the workload and still be able to be the beneficial during the interaction? That's the robot's function here, right? And the same thing actually also applies to industrial automation. So in the industrial automation, how do you make it accurate? How do you make it fast? And how do you create a system like the vision system that is not dependent on situations where your lighting is low, so your vision system doesn't work? How do you mitigate these issues? So these are very challenging problems in this field of robotics. Also, the robot operating system is one of the up-and-coming software framework that is being used widely in the robotics community. The benefit of using a robot operating system, it's a Linux-based framework that you use, is that it actually allows you to tap into the previously defined or previously designed modules, which basically allows you to not reinvent the wheel, but to move on and move forward by using what has been developed in the past and then move forward. So for example, if you're building a QR reader, right? So you will spend like a month or a month and a half on getting into the vision system, decoding the QR code, and how do you make that QR reader? This thing is already available. So it's like off-the-shelf available robust solutions that the robot operating system, you can just tap into that and build your next system, which basically after you read the QR code, what are you going to do next? If you're going to move, if you're going to go pick up an object, depending on the data on the QR code. So that's just one of the examples. It actually has navigation systems, a navigation stack already there that you can implement on any robot. And these are very beneficial. So if you're working in robotics, I would highly recommend checking this robot operating system out, which is being used by Baxter. All the robotics community right now are using it. Having said that, I would like to thank you again for inviting me to this talk, and I'm free to take any questions.
Thank you very much. Thank you very much, Satulas. So it's very much informative, as well as exhaustive, and I think you have also thrown some light on the recent state-of-the-art robot what is going on, and that is also in connection with the how a robot can share with the humans' functions. So we are actually privileged to have with us our Pro Vice Chancellor, Dr. Professor PK Mando with us. So, sir, namaskar, sir. Sir, can I have some words from our Pro Vice Chancellor in response?
You want to speak me something? Okay.
Yes, sir.
I joined maybe 5-10 minutes late, so I missed some of the interesting human interaction part. But it was really very interesting. I wish to listen to how innovation working in industry, and I think the beginning, the first this series lecture was good. It was very interesting. And you may, I think we may invite Dr. Das again for some detail in maybe small part with more elaborate discussions of the packaging systems. That would be very nice, and it was a nice, I think, presentation, and very practical, linking with the theoretical research that of the practice, and particularly I very much appreciate the practical application of that adaptive robot, and a lot of other innovations I could guess they have done, and the human interaction part was also quite interesting. So I think in the university we are trying to build a I think robotics center in future, I request Dr. Das to help us as and when we require. Because we are trying to also, our students have participated in robotic competitions. Nevertheless, the university, we wish to have a robotic center where we'll carry out the research, pulling people from mechanical, from computer science, from electronics and electrical engineering. So we want to build a really center. I think you have enough expertise, you have a rich experience, and I think we'll request you to, I think, get your guidance in future while building up the robotics center. I think
Yeah, definitely.
that's one of the very fantastic thing I received. I think I thank the organizer very much. I think thank HOD, Dr. Bibu Mahanti, and also Dr. Gyana, who could arrange such a nice lecture in the beginning of this series. That's very fine, and it is quite memorable. Thank you, Dr. Das, to share your time and share your expertise with all of us. Thank you.
Yeah, no problem. Thank you so much for inviting me.
Thank you, sir. Thank you very much. Thank you, Dr. Das. As Sir has told, we must look forward for more interactions with you regarding setting up this particular center for this robotics in our university as well as institution. And thank you very much once again. Thank you all the participants over here, all the audiences for your time over here. And this is our inaugural session, and I think that we will continue with this session for hopefully at which weekend on Saturday at any time again to the presenter over here. And I am looking forward. I request Dr. Das once again, if time permits, I will to you once again for another presentation for this. Thank you, Jana. Thank you all the faculty members present over here, all the professors, deans, and other members, all the thank you very much. Thank you.
Yeah, thank you.
At the last, I would like to thank Bishant and the SOA NSS group who have put forward their effort to stream this small meeting into a YouTube stream. So thank you very much.
Okay, thank you also. Thanks to the students also, students volunteers also from my side also. Yeah.
Thank you, Dr. Das, for such an entertaining talk. Okay.
Yeah, no
Thank you
problem.
all.
My pleasure. Yeah, thank
So
you.
let us take leave of this particular meeting. Thank you all.
Thank you all.
Recording stop.
Yes.
जरा मो कैमरा टा कोणला अंदर काही बंद है ला पे
Just a second. Vishant, can you switch off the... Vishant, can you stop the streaming?
Bishant is not there. I think he has left already.
Then who would stop the streaming? So NSS is there.
जानो हेलो
हाँ सर
अरे मो कैमरा टा कहीं हटक
किंवा किछि समय परे चेष्टा करंतो
कैमरा टा
आज्ञा सर
मो कैमरा टा
स्ट्रीमिंग ऑफ कर दिया
श्योर सर मैं ऑफ कर दूं
सर ताको आउथरे यूएसबी रू बाहर करके एंटर करना
चालते हटक मजूर गट्टी गला हम कहू तो ओके थैंक
हाँ असली सर Sir, shall we stop this meeting?